right? Structures of crystalline solids. So these are the issues we are going to address in this particular chapter. How do atoms assemble into solid structures in metallic, ceramic, and polymeric materials? So you know the arrangement of atoms in each material is different from one to another, right? How do the structures of ceramic materials differ from those of metals? So due to these arrangements of atoms, how do the structures, the properties will differ for one metal to another metal? No, not a metal, one material to another material, maybe from ceramic to metal, metal to polymer, something like that. How do polymeric crystal accommodate the polymer chain? You know, polymers, they are a chain. They are not a monomer, they are polymers. So that is many monomers joined to have a polymer, right? And then how does the density of a material depend on its structure? So you know the arrangement of atoms determine most of the aspects of atom. Two arrangements are shown, right? Considering this radius as A for both, can you calculate what is the percentage of the solids to this void? Right, percentage of solid to this void, right? So this is just to give you a brief idea of what we are going to do in the chapter, right? Throughout this chapter, what we are going to do. So we are going to calculate, because in the first slide I told you about the objective. So we are going to determine how these atomic structures, their designs, difference between metal structure and ceramic structure and different things, right? Right, metallic crystal structures tend to be densely packed. You know, usually metals compared to non-metals have higher density, right? Usual case. There can be exceptions, right? We don't go into extremes. So density of metals are usually higher than density of non-metal. So tend to be densely packed if the number of atoms in a particular unit volume. So from here onwards, I will use the word unit volume, unit area, something like that. So unit volume mean one unit, right? This is unit area. If it is volume, then that will be 1 unit into 1 unit into 1 unit, that is unit volume. So in metallic crystal structures, atoms tend to densely packed, right? So the density is high. Reasons for dense packing. So why is it that typically only one element is present, so all atomic radii are the same. So if it is metal, then if it is sodium, then it is only sodium throughout, right? There is no sodium and potassium, so that is only sodium mean the atomic radius of that particular atom will be same, right? So only one element is present, so all atomic radii are the same. I am talking about metallic crystal structures. Metallic bonding is not directional, right? Metallic bonding is not directional. There are bondings which are unidirectional, bidirectional, and we'll call them as different names, right? So now we don't need them. They are not directional. So which means it does not need that only in this direction this will form bond, this direction it will not form the bond, something like that. That is not the case, not directional. Nearest neighbor distances tend to be small in order to lower the bond energy. So at the start of this subject, I told you, usually elements tend to have lower bond energy by staying at the lower state, energy state, right? So neighbor distance tend to be small in order to keep the bond energy low. So if they stay together, right, as a pack, the energy would be low to keep them. If one is standing here and another one is standing here, then you know we need to spend a lot of energy to keep them in that particular space. But if they are closer together and as a pack, we don't need to spend much energy on that. Electron cloud shields cores from each other. So electron cloud, since this is an atom, we will have electron cloud. Shields cores from each other. So they form a kind of cloud. I told you electron has two nature. One is particle nature and one is wave nature. So that will be in a cloud, in a possibility area, right? So that cloud try to shield. Shield mean, you know, to cover or to, yeah, something like that, from each other. These are the reasons for dense packing. Have the simplest crystal structures. So metals, they have simplest crystal structure. They are not complicated. And we will examine 3 such structures. So in metallic structures, there are 3 prominent structures. Now we will see one by one, right? First one, this is simple cubic structure, right? Simple cubic structure. SC, we call it as SC. So in this red diagram, there you see a kind of this box is drawn in a lighter lines, you see. Okay, so this is 3D, you see. This is one face, if you assume as front face. This is side face, and that is back face. This is top face, this is bottom face, right? So these will form bottom face, these will form top space, these 4 will form front face, these 4 will form side space, right? So this is a 3D structure. Can you imagine this structure is actually being here? This line here, this line here, this line here, this line here, this line there, right? This structure is known as simple cubic structure. All right. So this is how you have seen, right? This is the diagram which I have shown in the left side. So that's a cube, and this is how this cube is formed. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. By these 8 atoms, you see 1, 2, 3, 4, 5, 6, 7, 8. This is formed. All right. Pay close attention to these quarter pieces. You see this quarter piece, and all, right? So now, by these lines, right? By these lines, the volume enclosed is only this much. So you see, these are 4 atoms, which are actually 1, 2, 3, 4, 5, 6, 7, 8. Now I am going to join them with the same link like this. Okay, so from here I will draw like this, I will draw like this, and like this. So now this part is complete. I have joined 4 atoms with 4 lines. Now this, and this, right? So this part is now complete, and now I will complete this and this. This one I will draw in dotted line, because since that is in the other part, you cannot see actually, right? All right. So I have drawn this particular diagram as this diagram, right? Now, the volume enclosed by the lines which I have drawn, you see the lines which I have drawn, if I actually cut them, that will look like this. So here and here, due to this line and this line, 1/4 of a complete molecule will be removed, right? So by this line and this line, you see this and this particle is removed. Similarly here, right here, from this line and this line, all right, this part is removed, right? So that is this part. From this line, and this line, you now see this part is removed. Similarly here, 1, 2, 3 these lines, this part is removed, right? So similar case will be applied for these 4 structures also, these 4 atoms also, right? So what I want to show you is 4 atoms and 4 atoms. Totally 8 atoms are there in simple cubic structure, first thing. Okay, and those are in contact with each other, right? And if you see, when you draw a cube considering all for all 8 atoms, that cube will enclose only these parts. So this atom now will be something like this. Okay, if I assume this atom as this will be the atom, right? Similarly, this atom will be something like this. This atom will be something like this, and here this will be something like this, right? Similar case in the back side also. So front side 4, back side 4. So now see, if I draw this one completely, I can obtain this diagram, right? So by drawing these lines, I can say in unit volume, right? So that's why I told you about the unit volume. So here unit volume means this length is 1, this width is 1, depth is 1. All right. In unit volume, how many atoms I can have and how much is the empty space I can predict, right? So this region where we don't have any atoms is the empty space. This region where we have the atoms are the parts where the atom will be located, right? So why I do this is to calculate in unit volume how much percentage is occupied with the atom and how much percentage is empty. You take like 8 small balls which can be cut, or even 8 limes are fine. You take 8 lemons and arrange them in a way so that you can see. So what you have to do is you arrange those 4 limes, right? Insert a like metal rod through the center, only through the center, through this center to that center, that center to that center, like that. Okay, and then along that metal rod you cut them, right? You cut them and see in the cube, right, in the unit cube, how many lemons you have. Or else if you don't have 8 lemons, you can do one more thing. You take 1 lemon, okay, and cut it into 8 pieces. 8 pieces means each piece should have a shape like this, okay, and arrange them in a way like this. Okay, arrange them in a way like this. All right, and then you draw a cube beside that, right? And then calculate how much is the space occupied by the lemon and how much is the empty space. So if this idea is to those who still face difficulty in understanding this one, right? Now I need to find in unit cube how much percentage is actually occupied with the atom and how much percentage is empty void. So we only concentrate on this region. So unit cubic structure 1 by 1 by 1. So we can calculate the volume of that unit cube, draw 1/8 of one sample. So you can calculate the volume of that. So if you reduce one from the other, you will get the final answer, right? So when you see this one, you see here 1, 2, 3, 4, 5, 6, 7, 8 pieces of 1 into 8. So the pieces which are already aligned like this, right? Aligned like this is now taken into you see 1, 2, 3, 4, 5, 6, 7, 8 pieces of 1 into 8 length. So these 1 into 8, now you see 1 by 8, 2 1 by 8 forming now 4, right? These 4 1 by 4 forming 2 1 by 5. You see this 1 by 4 and this 1 by 4 forming a half, this 1 by 4 and this 1 by 4 forming a half, and this half and this half is now forming a full object. You see, So actually in this cube, right, in this cube, the volume occupied by all these 8 atoms is actually the volume of one atom, right? 4/3 pi r cube, right? Here you know this is length into width into height, right? So if you have the volume of this, right, volume of cube, if I say length into breadth into height, and volume of cylinder, that is equal to 4/3 pi r cube. All right, 4/3 pi r cube. Now I need to find how much is this void space is. So there I will subtract the volume of cylinder from the volume of cube. That will give you the volume of empty space. All right. So LBH minus 4/3 pi r cube will give you the empty space. All right. So this R will be given, right? This R will be given. You need 4/3 pi r cube, no? So 4/3 is a number, pi is a number, r cube. R I will give. So you can find the volume now. So in this one cube, you have 8 pieces of, right? 8 pieces of atoms of 1/8 of each atom. So now we have 4 plus 4, 8. You know, structure atoms 4/3 pi r cube. All right. If I consider one side of the cube as A, unit volume A, right? Unit volume A. So which means the volume is A into A into A. Is that thing okay? Volume of cube is equal to A height into A length into A, that is width, that is A cube. Is that okay? Similarly, volume of sphere, right? Sphere is this one. So you have seen that is one sphere at all. So 1/8 into 8 pieces. So 1/8 volume into 8 pieces of structure atom. So that is one atom. So volume of sphere is 4/3 pi r cube. Now r, you know, this is A, right? This is A for the cuboid. In 1A there is 2 r, right? You see 2 cylinders, 2 sphere parts are here. So I can say this as r and this as r, right? So from there you can say A is equal to 2 r, right? Because here one atom, here one atom, 2 atoms making 1A, that is A is equal to 2r. Then r is equal to A by 2, that is 0.5 A. Okay. Now I will put this 0.5 A into my equation. That is 4/3 pi r cube. R is 0.5 A cube. Sir. All right. So I'll substitute this R with 0.5 A whole cube, right? So that will give you 4/3 into pi, you know, 22/7 into A cube into 0.5. So 0.5 into 0.5 into 0.5, how much? 0.25, 0.125. 0.125 A cube. All right. Now you see here, one atom into found 1/4 pi A cube. I don't need the exact value, but I just need the ratio, right? So if I divide this with this, that's what happened here. This value is here and this value is here, right? So 4/3 pi A cube divided by A cube, that will give you 0.52. So your a cube and a cube will be cancelled, right? At the bottom you have 1. At the top you may have 4/3 into 5 into 0.125. 125. So if you substitute, you will have 0.52, right? So here in simple cubic structure, right? In simple cubic structure, the ratio of atoms to the ratio of void space is 0.52. So here in the simple cubic structure, only 0.52% of the volume is filled with atoms, while 0.48 rest of the percentage is empty. All right. Now I am going to introduce you certain terms, right, which is accompanied with this calculation. Now we just have said radius and volume and cube and sphere and all, right? So now I am going to introduce you certain terms which are accompanied with. Here you see APF, atomic packing factor, right? APF we call it shortly, atomic packing factor. This atomic packing factor is given as volume of atoms in unit cell over volume of unit cell. You need to understand the difference between these two. Volume of atoms in unit cell. So that is this atom, this atom, this atom, this atom, this one, this one, this one, and this one. Right. So volume of atoms in unit cell divided by volume of unit cell. Volume of unit cell is this into this into this. This is the volume of unit cell. Right. So this A cube is the volume of unit cell, and here this 4/3 pi r cube is the volume of atoms in unit cell, right? So what you have calculated so far is known as atomic packing factor, right? So atomic packing factor for simple cubic structure is 0.52, right? So while we are calculating, we never go into these names. Now I am introducing the names, right? If I introduce the names by that time, that will be complicated. So what you have calculated as the volume of atoms in unit cell over volume of unit cell is 0.52, which is known as atomic packing factor for simple cubic structures. Okay, we are talking only about simple cubic structure by now. Closed pack directions contains 8 into 1 by 8. So this 8 into 1 by 8, we have 1, 2, 3, 4, 5, 6, 7, 8 atoms, right? 8 atoms. They are not total full atom, just 8 atoms, and 1 by 8 of each atom is actually incorporated here. So this particular region is 1/8 the volume of a one sphere, right? Rare due to low packing density. Only PO has this structure. So rare due to low packing factor. So this structure, right, simple cubic structure is existing only on polonium, right? Polonium. Close pack directions are cube edges. Coordination number 6. So this coordination number means an atom, any one of this atom, right? Any one of this atom. It need not to be this atom or that atom or this atom. Any one of this atom forms contact with how many other atoms, right? So if I take this atom, right, this is in contact with this atom, right? These are in touch. This is in contact with this atom. These are in touch. This is in contact with this atom. Okay. And if I place another layer here, oh no. If I place another layer of atoms here, right, this will be in contact with the atom on the top also, right? So this atom also it will be in contact with. And this will be in contact with an atom which is on this side, right? I can draw certain atoms to this side also, right? So this is going to be like this. Throughout this one, I can draw atoms like this. Similar way here also I can draw atoms like this. Downward also atoms I can draw. So this is a continuous structure, okay? Just for the sake of easiness, we take 4 and 4 atoms to explain you, right? So if this red atom, right, this red atom is your this atom, if I assume this as this red atom, so this way one, that is this one, right? This white one, that is this one. Top side one, that is this one. This side one, that is this one. This side one, right, in front of all the atoms, no. So that is this atom, and in the bottom side one, that is this atom, right? So totally an atom in simple cubic structure can be in contact with 6 atoms, right? I repeat, in simple cubic structure, any arbitrary atom can be in contact with 6 atoms, right? I am talking about contact, so this and this should touch, they should share the surface. This and this are not in contact, right? This and this are not in contact because in between there is a void. You see here and here, that is not contact because there is a void, right? But this and this are in contact. You see here, there's a contact, right? So coordination number is 6 for simple cubic structure, and the meaning of coordination structure is nearest neighbors, or the atoms which are in contact, right? Nearest neighbors or the atoms which are in contact. And usually these distances will be equal for all 6. So this, if I consider this as distance A, this one, here, here, all distance will be A probably, right? So the coordination number is the nearest neighbors which are in contact with each other. So for simple structure, simple cubic structure, the coordination number is 6. So what actually you are seeing at the moment is about simple cubic structure, okay? SC structure. So 1 2 1 2 1 2 1 2. There's no body and all, right? This is simple cubic structure, right? You see here, there is nothing in the body, so that is simple cubic structure. In this one, right, there is a pink atom and there are 1 2 3 4 5 6 yellow atoms. All right, this is for the coordination of the coordination number of the simple cubic structure, right? There you see this pink atom is in contact with only these 6 atoms, right? So that's why the coordination for simple cubic is 6, right? So if I can draw, so this pink is in contact with 1 2 3 4 5 and 6, right? So this is for the coordination number of the simple cubic structure 6, right? This is known as body centered cubic, right? Body centered cubic. So by name, right, by name you can see there's a center body, right? This white one, that white is actually complete inside, right? That white is completely inside. That is what it is called as body centered cubic structure. Body is in the center, it need to form cubic structure. So how come the possible close packings, right? Close packings. This is known as BCC, body centered cubic, right? Here you see the touching of these atoms, the contact, right? They are not as like in the cube, a simple cube, they are different now. So this white, if I assume this is in contact with this red, that red, the behind red, and there is also another behind that red also, and similarly here this one, this one, this one, and that one, right? So this is in contact. I mean it is touching these four. You see this body center, this big one, which is in contact with this one, this one, this one, as well as this one. Similarly here, 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 and the other side, right? So here the coordination number is 8 because 1 2 3 4 5 6 7 8. The nearest neighbors are 8, right? So 8 atoms are touching, one atom is touching 8 atoms. So here the coordination number is 8. So atoms touch each other along cube diagonals, right? Cube diagonals. Diagonal, you know, if it is a cube, then this and this we call it as diagonal, right? So this way and this way we call it as diagonals. So here they are touching each other in diagonals, right? Not all atoms are identical. The center atom is shaded differently only for ease of viewing, right? So the first diagram you see here, that is a white atom, and then there are few red atoms, right? So in nature all atoms are similar, right? There's no red and white. I just need to show it differently, right? Otherwise, if this one also in red, I can't show the coordination and all, right? So for that purpose it is drawn differently. Otherwise these all are identical. Example: chromium, tungsten, Fe, alpha, tantalum, molybdenum. So metals which can take this shape, body centered cubic, is chromium, tungsten, alpha, Fe, right? In Fe is iron, you know. Then tantalum, molybdenum, right? So these all will take BCC structure, that is body centered cubic structure. Coordination number 8. In iron we have different phases, right? So alpha is there, delta is there, gamma is there, right? There are two. BCC structure will only be taken by FeI alpha, right? Alpha ion will only take this structure. And now number of atoms, right? Number of atoms. Here it is 1 center and 8 corners. This is one body centered. 1, 2, 3, 4, 1, 2, 3, 4 each corners, right? So just for the easiness of the diagram, they are placed this far, but that is not the case. They will be like close as it is, right? Okay. Right, you see here. So body centered cubic. These all are in each diagonals, but that there's a body centered cubic. If I draw a line, right, through the centers of these 8 atoms, right, through these 8 atoms, this is going to be like this. Draw a cube consisting of all these 9 atoms. This is how it is going to be, right? You see these two here, these two here, those two at the back of this one, and these two at the back of this one, right? And there's a center atom that is at the center. You see, in this type of unit cell, the constituent particles occupy the 8 corners and body center. 8 corners and center body, right? Right? 8 corners into 1 by 8 per corner. That is 1. And then this one, right? Right, so in the corners there was one complete one, and you see 1, 2, 3, 4. These 4 now will form 2, and these 2 will form now 1, right? So the corners will form one sphere, and inside the body there is one sphere, right? So that is totally 2 spheres. So now 8 corners into 1 by 8 per corner, that is 1 sphere, and 1 here, yeah, 8 into 1 by 8, that is this sphere. And then I have this body center cube, that is 1 sphere, right? So these at the corners 1, 2, 3, 4, 5, 6, 7, and at the back side 8. These 8 will form 8 corners into 1 by 8, that is 1, right? So this is 1, and in the middle the body there is 1, that is this 1. So this 1 plus 1, that is equal to 2, right? So in body centered cubic structure we have 2 atoms per unit cell, right? 2 atoms per unit cell if I consider this as the unit cell, right? If I consider this as a unit cell, all right? Coordination number. So this is our body center atom, right? So here only the centers are marked, okay? This one is the center of this atom, this is the center of this atom. Similarly, only centers are marked. So here 1, 2, 3, 4, 5, 6, 7, and 8. So one atom is in contact with 8 atoms. So here the coordination number is 8. Now we will go to the APF, that is atomic packing factor. How to calculate the atomic packing factor of BCC, body centered cubic structure. APF for a body centered cubic structure. Now we are concentrating on diagonals, right? Because I told you these atoms are in contact in diagonals. You see here, this one and this one is not in contact in this region, right? This and this are not in contact with this region. So as like in simple cubic, we can't say two atoms are sharing one edge. In simple cubic structure, this was the case. R is equal to 0.5a. But here, since there is a gap between these two, this is not applicable, right? So now we need to see where can we obtain these dimensions. So we need to check where and through which line these are in contact with each other. So in the previous slide, I told you they are in contact with each other in a diagonal form, right? So diagonal means here to here. So let's see, this is given as A, all right? This is given as A, that is for unit cell. So I will obviously take that one as A. And then I have this, also this, all right? Here you see, this is complete one sphere in the body, right? Complete one sphere in the body. So I can have that as 2r, right? One, if r is radius, then 2r is the diameter, right? So this length from here to here, I can assume it as 2r, right? Then I told you these 8 are forming 1/8 of the simple atom, which means here to here, right? The length is r, and again here to here, the length is r, right? So this is the center of this atom to the touching point of this atom, that is r. Similarly here, the center of this atom to the touching point at this atom, that is r. In the diagram, I told you this is A, right? This is A, and this is also A, right? So I can find this length from here to here, that is under root of a square plus a square, that is a square plus a square, which is equal to root 2a, all right, 2a. So this length from this point to this point, if it is root 2a, that is this root 2a, right? And I already know this length is a. Now I have 4r here, so 4r I can put it into Pythagoras equation. 4r square is equal to this square is equal to this square plus this square. That's what Pythagoras equation is like. So this square, that is a squared. This one root 2a whole squared. So when I solve, so here I have 4r whole squared. Here I have a squared plus root 2a whole squared, that is 2 root 2 square 2 a squared, that is 3a squared. So if I take root under root of 4r square, right? If I take under root of 4r square, then that square and this square root will cut out. 4r square under root will be equal to 3a squared under root, right? In that case, so this square root and this square will cut out. So I have 4r equal to a squared root 3a into a squared, that is a, all right? So now 4r is equal to root 3a. You see, now I will substitute that one into our normal equation, 4/3 pi r cube into 2, because I have two atoms here, 1 2, so that is this 2. Don't forget to bring this tau here. Simple cubic structure, that is 1, so I have 1 here. In body centered, I have 2, that is 2. 4/3 pi into r. I told you root 3a by 4, right? If 4r is equal to root 3a, then r is equal to root 3a by 4 whole cube. So that will become 2 into 4/3 into pi into, that is 22 by 7. Here I have an a cube, here I have an a cube. This will cancel out, right? So I have root 3 cube by 4 cube. 3 into root 3 by 4 cube. 4 cube 64, right? So this will give you 0.679, okay, 68. So here in body centered cubic structure, the atomic packing factor is 0.68, right? 0.6768, okay, right? So this is how we calculate the APF, atomic packing factor, for BCC, body centered cubic, right? Now I have body centered cubic, right? So there is a blue atom which is the body, and we have 4 and 4, totally 8 atoms as the diagonals or corners, right? While it is rotating and all, right? So the green is the center and these blues are the diagonal. You see there's a cage like structure at the out, right? So this is the central atom body, and these are 8 atoms which are at the corners, so we can draw through it, right? Third structure, right, it is called as face centered cubic structure, FCC, right? So this is the arrangement, right? So again, this one by name, right, the center of these faces are the faces of the atoms, right? So if you consider this cube, these certain atoms which makes the face, right? So this in this face, this one in this face, all right, this one on the other face, here this one 4, this one 5, and this one 6, right? So 6 faces of the cube is made by 6 faces of the atoms, right? 1 2 3, opposite to this side 4, opposite to this side that way 5, and opposite to this way 6, right? And this is why it is called as face centered cubic structure, FCC, right? Face centered cubic structure. If you remember the body centered cubic, in that one the center is occupied by a single atom, which is the body of the atom. But here the faces are forming the center, so it is called as face centered cubic structure, right? Atoms touch each other along face diagonals. So here you see along the face diagonals atoms touch each other, right? So this atom and this atom and this atom, these are in contact by the diagonal of the face, right? In the body center, you remember that is diagonal of the body from that corner to this corner inside the body, right? This is how the body centered cubic structure made up of. But here the face centered cubic, the diagonals of the face are in touch. All atoms are identical, right? So this sentence I am putting in all slides because just to make sure the difference, because if I put everything in red, then that won't look nice, right? It's difficult to understand. The face-centered atoms are shaded differently only for ease of viewing. So the atoms which are shaded in white, right? This one, this one, this one, these are the atoms which show the face to the center of the cube, right? So if you consider this face of the cube, all right, the face of this atom is centered, right? If I consider this face of the cube, then the face of this atom is centered, right? If I consider this face of the cube, the face of this atom is centered, right? So just for the ease of understanding, I have these face centered 6 atoms in white color, but in nature all atoms are similar in structure, all right? Example: aluminium, copper, aurum, that is gold, plumbum, lead, nickel, platinum, Ag, argentum, that is silver, right? So these are few examples for this FCC structure, face centered cubic structure. And now the coordination number, right? So coordination number, I told you the nearest atoms which are in contact with each and every particular atom, right? Nearest atom. So let us see how is this 12, right? So say for example, I'll take this atom, right? This atom in the top surface. So this one, 1, 2, 3, 4, 5, 6, 7, 8. Similar to this, in the top also you will have 4 atoms, right? So on this place I will have 1. On this place I will have 1. On this surface I will have 1. And on the backside this surface I will have 1, right? So now I have 8, 9, 10, 11, 12, right? So this is the coordination number 12, right? Any doubt in this coordination number? Is it clear how the coordination number is made? Yeah. Who is that? Okay, again. Right. So now I have a cube. So to support my drawing, I will draw another cube. Okay. You need to assume that as a cube. Since these diagrams are in green, I will also draw in green. Right. So in this cube, I have an atom here. Right. So in this cube also, I will have that atom here. Here I have atom in this phase. So in this phase also, I will have an atom. Right. In this phase, I have an atom. So in this cube, in this phase also, I will have an atom. In this phase, I have an atom. So on I'm drawing in the back phase, right? So here also I will have an atom. So these atoms, they will also be there. So we don't need them for our drawing of this coordination number, right? Now we will see. So I told you the closest atoms for a particular atom, right? So if I take this atom as my reference atom, right? 1, 2, 3, 4, right? These 4 are in this phase. Then 5, 6, 7, 8, right? These are in this plane. 9, 10, 11, 12, right? So probably these will be in a plane. This may form a plane. This will form a plane. Probably at the mid of this cube. All right. So like this. Right. So all these distances are equal. Right. All these 12 distances are equal. Right. So this is how we draw this coordination number. Right. So in this plane I have 4. On this cube I have 4. And on this cube I have 4. That is totally 12. Any other atom than these 12 are far from the surface. So if I take this one, for example, if I take this one, right, this is far from all these pink lines, right? Similarly, if I take this atom, right, it is far from all these pink lines, right? So this is how the coordination number is made. The nearest atoms, right? Nearest atoms to a certain particular atom. Right. So this is our face-centered cubic structure, right? So I remember use the same diagrams, right? You see, this is the face-centered cubic structure. So this is a unit cube, all right? Unit cube. So there will be number of cubes on this side, that side, top. There, this is a continuous. For the just the exam explaining purpose, we have taken one particular cell, and it would be easy to explain, right? So there you see there are number of atoms, and these all are in a unit, right? So this is how it will form inside the cube, right? So when you cut them along the face of the cube, right, that will form something like this. So it will form something like this, all right? So if it is as a bundle, this will look like this. And when you put the cube and cut it accordingly, this is how it will look like, all right? So now we need to see how many atoms are there, right? How many total atoms are there. Here you see this is a face, right? So we have 1, 2, 3, 4, 5, 6 faces. You know, the cuboid has 6 faces. In each face, we have half atom. You see, half atom is there in each phase, which means 6 into half, that will give you 3, right? 6 phases, right? 1, 2, 3, 4, 5, 6 phases. The cuboid has 6 phases, and each 6 phase has an atom, all right, and 6. So these 6 atoms into half. Why half? Only half of the atom is there inside the cube, other half is outside, right? So this is a half atom. 6 into half plus, as like in the simple cubic structure, we have 1, 2, 3, 4. Similarly on the back side also 5, 6, 7, 8, right? So that 8 into 1 by 8. So that will give you 4 unit cells, right? This is a edge, no? So that is 1 by 8. So that will give you 6 into half 3 plus 8 into 1 by 8 1. If you add these two, that will give you 4 atoms. Right? 1, 2, 3, and 4. So here we see 1, 1, 2, 3. On the bottom face, I have 1, 4. Backside face, I have 1, 5. Backside of this, I have 1, 6. So 6 atoms of half, right? Because only half is there. And I have 1, 2, 3, 4, 5, 6, 7, and on this side 8. So I will have 8 into, these all are 1 by 8 size, right? So that will give you 1. This will give you 3. So altogether we have 4 atoms in a unit cell. 4 atoms in a unit cell. 6 phase into half plus 8 corners into 1 by 8. Now we will see how to calculate the atomic packing factor, APF, right? So atomic packing factor, I told you the equation, right? So volume of atoms in a unit cell over volume of unit cell, right? Here we see this is the arrangement of the atoms in that particular unit cell. So 1, 2, 3, 4, 5, 6, 6 faces and 8 corners. As usual, we will take an edge as A. Since these atoms are touching in phase diagonals, we need this length, right? We need this length. If you remember in the body centered, we took length from here, this corner to this corner, because it is connected through the body, right? This was in touch with each atom through the body. Here it is in contact with each atom by the diagonal of the face, right? So we can take this as A, and this is also A, right? This is a cube. We know length A, width A, and height A. I need this length. So as you know, if this is A and this is A, this is root 2A, right? So as per Pythagorean relation, this is A, so A squared plus this is A, that is A squared, under root will give the distance, this one. So I'll take the distance as AB. So AB is equal to A squared plus A squared, 2A squared. So under root 2 into A squared A. Alright. So this distance is root 2A. This is R. R is the radius of a particular atom. So along this diagonal, right, I have 1 R for this corner atom, another R for this corner atom, and 2 R for this half atom. So R and R, right? So root 2A equal to 4R. Alright. This is root 2A. We have calculated it based on A. Now we have R, 1R, 2R, 3R, and 4R. Right. So now R is equal to, this 4 will come down, root 2 by 4A. Okay. Root 2 by 4A. So this is the R. Since we have R and A, we will put it in the equation, right? So equation, as we know, unit of, not unit, number of atoms into volume of each atom. Right? So number of atoms we have already found, 4 atoms are there in this unit cell. So this 4 into, now volume of a sphere, 4/3 by R cube. R is root 2 a by 4, that is root 2 a by 4 whole cube. This is volume of atoms in the unit cell, right? And below that we have volume of the unit cell, so that is a into a into a, that is a cube. So this a cube and that a cube will be gone. So probably I will have 16 pi by 3. Here I have root 2 by 4 whole cube. So that is 2 root 2 divided by 4 cube, that is 16 into 4. So I will remove this 16 and this 16. This 4 and this 4 will be cut out. So I will have root 2 pi upon 6, 0.74. Okay, APFO, face centered cubic structure, is 0.74. So which means the total volume of the cube, right? In the total volume of the cube, 74% is occupied with the atom. You don't need to worry about this 2D diagram, right? Just see a 3D diagram. So this is how an FCC unit cell is formed of, right? So this ABC and blue, green, yellow, you don't need to worry about this. You don't need to, right? This is just to show how these atoms are arranged, right? So here one face, 4 corners, right? One face, 4 corners, one face, 4 corners, right? So in whichever the direction you see an FCC atom, you will see an atom's face on the body face of the cube, and there will be 4 corner atoms, right? Okay, then I have one more. So these green atoms, they will be on the top and the bottom. These 3 blue atoms are there, right? So they will be in the body but on a particular surface, right? So these will not at the edge, right? But this is in the face, right? So this blue is in this face, this blue is in this face, because this is a face, right? And this blue is in this face, but all these are in the corner, right? So this blue, if I take, this blue is in this face, right? Similarly, this blue is in this face. All right. So this is how the arrangement of HCP structure is. This is, so here you see top layer, middle layer, and bottom layer. Now we'll see the coordination number, right? So coordination number, I told you, the nearest number of atoms which are in contact, right? So I will take this as the reference. Okay, this as the reference. So now I will draw the coordination number, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, and similar to these 3 on this part also we will have 3, right? So 9, then 10, 11, 12. So as I told you, this is a continuous structure. Just for the easiness, we have taken only one cell, but this is a, so on these 4 faces also we have one here, and one here, right? So altogether 12. 1, 2, 3, 4, 5, 6, 6 in this face, 7, 8, 9, 9 in this plane, 10, 11, 12, 12, 3 in this plane, right? So altogether 12 is the coordination number. And cadmium, magnesium, titanium, and zinc are the examples for this HCP, that is hexagonal closed pack structure, right? Since we don't mention anything like C upon A in the previous things, because that's a cube. You know, a cube, all the dimensions are equal, right? Length and width and height are equal. But here this is hexagon, so that is not the case. So here the C, that is length of a side, upon A, that is length of the side of a face, will be equal to 1.633, right? This will be equal to 1.633. We didn't mention anything about the C upon A in the previous cases because they all are cubic structure and we don't need them, right? So this is a kind of special structure, and that's why it is less common.